afternoon to all. So this is the lecture 5. This is in which decimation and interpolation topics will be considered for the subject digital signal processing KEC 503, and I am Dr. Amit Garg, associate professor in EC department of AKGEC. Okay, so let us start with the topic. What is decimation and interpolation? Basically, decimation is the process by which we can reduce the sampling rate of a given system. Okay, and also interpolation is the technique by which we can increase the sampling rate of a given system. Okay, so these two topics, these two techniques comes under the category multi-rate signal processing. Okay, so first of all, we will see what do you mean by multi-rate digital signal processing. In short, we can call it as MDSP. So we will see the introduction. So we will see in many practical applications for digital signal processing, one is faced with the problem of changing the sampling rate of a signal, either increasing it or decreasing it by some amount. So this is basically the requirement. We want to change the sampling rate of the system. Okay. So the process of converting a signal from a given rate to a different rate is called sampling rate conversion. So sampling rate conversion is the method by which we can convert the sampling rate of a system sampling rate of a system to another rate. Okay. So in turn, systems that employ multiple sampling rates in the processing of digital signals are called multi-rate digital signal processing system. Okay. So let us suppose we are having a system and we can change the rate of that system or the sampling rate of that system. So then it is called multi-rate digital signal processing system. Means multi-rate means we can change its rate, like initially its rate is, let's say, 10 kilohertz. We can change the rate as 5 kilohertz or 2 kilohertz or 20 kilohertz or 40 kilohertz. So that's why we are getting different rates. We can getting the different sampling rate for the same system. So that's why we can call it as multi-rate signal processing system. Okay. Discrete time systems may be single rate system or multi-rate systems. The systems that use single sampling rate from A to D converter to D to A converter are known as single rate systems. Okay, means there is no change in the sampling rate. And the discrete time systems that process data at more than one sampling rate are known as multi-rate systems, means in which we are changing the rate of the system from one rate to another rate. Okay. So different sampling rates can be obtained using an upsampler and downsampler. So basically, upsampler is a device and downsampler is a device. By using this upsampler and downsampler, we can increase the rate. And by using downsample, we can decrease the rate. Okay. So the basic operations in multi-rate processing is to achieve this are decimation and interpolation. Okay. So if you are using an upsampler, then basically with the help of upsampler, we can increase the rate of the system. And by using the downsampler, we can decrease the rate of the system. Here the decimation is used for reducing the sampling rate and interpolation for increasing the sampling rate. Okay. So now how can we explain this downsampler? So comes to the process decimation. Okay. So reducing the sampling rate of a discrete time signal is called downsampling. The sampling rate of a discrete time signal can be reduced by a factor d by taking every dth value of the signal. Like we can see from here, like we want to do the decimation, and the decimation factor is represented by d, let's say, and let's say d value is 2. So what do you mean by this? This is our original signal sequence 1 2 3 1 2 3 1 2 3, like this. This is our original sequence, and let us suppose we are using a decimation factor d equals to 2. So we can write it like n equals to, in that case we can write it like n will be represented by nd, where d is 2. So x2n means, if we have given xn, then if we want to calculate x2n, so x2n will be like, first value we will take, we will remove this value, then again we will remove this value, this value, like this. So we will get the output like 1 3 2 1 3. You can say if d equals to 2, then we have to remove d minus 1 samples between d minus 1, that will be equal to 1 consecutive samples from this. If we are taking x3n, means here d equals to 3. So d equals to 3 means d minus 1 value will be equal to 2. So we will remove every 2 values after between the consecutive values, like 1 3 2, you can see here. So this and this value will be removed. Okay. sorry, in this we will remove this value, so that we will get 1 1. You can take this xn, again I am writing here, so 1 2 3 1 2 3 1 2 3, okay, and you want x of 3n, so you will remove two samples between the consecutive samples, this and this and then this, yani we will get 1 1 1 like this. So x2n is obtained by keeping every second sample of xn, and x3n is obtained by keeping every third sample of xn and removing other samples. So this is how we do the downsampling. Okay. So mathematically downsampling, as we have seen, that it is represented as yn equals to x of d capital D times n, and the symbol for the downsampler is shown in this figure here. So if input sequence xn is there and we are passing it through a downsampler, so this is the symbol by which we will make a downsampler, an arrow pointing towards in the bottom direction and D written in the block. Okay, so this is the downsampler. So if we will take our original sequence xn and we will pass it through a downsampler, we will get the output yn, which is of this type. Okay. So decimation is the process of decreasing the sampling rate by an integer factor d by keeping every dth value and removing d minus 1 values between samples. Okay. So this is again I have represented using the graphical method. So here is the sequence xn. Now let us suppose you want to calculate x2n. It means you will remove this sample, this sample, this sample, this sample. Accordingly, you will get the output. For d equals to 3, you will remove this sample, you will take this sample, you will remove this, and you will take, so you will get these samples. Okay. Okay. So there is one difference between decimation and downsampling. Okay. So downsampling is an operation within the decimation. But what happened if we are having a sequence xn and we will do directly downsampling? So in the process of downsampling, definitely data will be decreased in the process of downsampling. But decimation will include one another block along with it, because if we are having a sequence xn and if we will directly downsample the sequence, then there will be aliasing effect. Okay. So for mitigating that aliasing effect, what we have to do, basically we have to band limit this signal first, and then we can perform the downsampling to avoid that aliasing. Okay. So you can see this decimation, we have to see decimation by a factor d. We will see that how we are having a sequence xn and we will perform the downsampling by a factor d. Then how the mathematical or the spectrum, how the mathematical analysis will be there, and basically how the spectrum is looking like, we will see all these things here. So what I am telling you that if we are doing this decimation task and we are simply downsampling only, then what happened? There will be a aliasing effect. Okay. So what we have to do for avoiding that aliasing effect? First of all, we have to band limit this input sequence xn. So you can say decimation is the process in which first of all we will pass our signal through a low pass filter, means xn will be passed through a low pass filter, and then we will pass it through a downsampler, and then we will get the output. So you can say if we will combine a low pass filter and a downsampler, then we can combinedly call it as decimator. Okay, and this process is called decimation. So decimation is basically the combination of low pass filtering and the downsampling operation. Okay. So now come to the topic decimation by a factor d. So let us assume that a signal xn with a spectrum x omega is to be downsampled by an integer factor d. Okay. So let us take, we have taken a sequence xn for which spectrum is defined as x omega, and we need to downsample this signal by an integer factor capital D. Okay. Now you know, because the sequence is discrete. Okay. Because the sequence is discrete, so if we'll take its spectrum, then it is periodic with period minus pi to pi. Okay. You can also write it x e to the power j omega. There is no difference here. Okay. But it is basically the DTFT of the sequence xn. For the simplicity, I am writing simply x omega. Okay. So the spectrum x omega is assumed to be non-zero in the frequency interval between 0 to pi, or equivalently mod f is less than equal to fx by 2. So your omega must be restricted between 0 to pi, okay, or you can also write sorry, it is mod of omega, so it is minus pi to pi, okay. So we know that if we reduce the sampling rate simply by selecting every dth values of xn, the resulting signal will be an alias version of xn. So this is we have already discussed with the folding frequency of fx by 2d. So to avoid aliasing, we must first reduce the bandwidth of the sequence xn to fmax equals to fx by 2d or equivalently to wmax equals to pi by d. So first of all we have to do this thing, okay. So then we may downsample by d and thus avoid aliasing. So before doing the downsampling, what we will do, we will reduce the bandwidth of xn, we will reduce this bandwidth of xn, which is actually x omega, by a factor d, so that the maximum frequency f max will be equal to fx by 2d. This is the folding frequency. So this aliasing problem can be eliminated by band limiting the input signal by inserting a low pass filter called anti-aliasing filter before the downsampler, okay. So the low pass filter that I am using, I have made this. So the low pass filter I am using here is nothing but anti-aliasing low pass filter, because it is used to reduce the aliasing process. It is used to reduce the aliasing process in the process of decimation, okay. So this aliasing problem can be eliminated by band limiting the input signal by inserting a low pass filter called anti-aliasing filter before the downsampler. The anti-aliasing filter and the downsample together is called the decimator, okay. So this is nothing but anti-aliasing filter. So what we have to do, basically in the process of decimation, we will take a sequence xn, then first of all we will pass the sequence through an anti-aliasing filter, which is a low pass filter, and then we will pass the output of this low pass filter into the downsampler, and as a combined low pass filter and downsampler is called as decimator, and this process is called decimation, okay. So this we can see that this is the decimation process. So this is called as decimation filter. This is decimation filter. It is your anti-aliasing filter. This is your low pass filter, okay. So you can say this is an anti-aliasing filter which is of low pass type, and it is also called decimation filter, having impulse response Hn or frequency response H of omega. So here is the sequence xn or the original signal xn. You can see this is the input signal. Here the rate is, let's say, capital Fx. Capital Fx is the rate. You can call it as 1 by Tx. Vn is the sequence that we will obtain by passing this sequence xn through a decimation filter of impulse response Hn. So what is the value of Vn? If we will see here, the operation is convolution operation. So xn convolution Hn. So Vn is obtained like this. Now what is the relation between Yn and Vn? Yn is equal to V times Md. Yn equals to V times Md, because this operation is because here the block is downsampler, okay. So the output Yn is obtained as Yn equals to V times Md. Now what about this filter? So the decimation process illustrated in figure 3, the input sequence xn is passed through a low pass filter characterized by the impulse response Hn and a frequency response Hd omega, which ideally satisfies the condition. So if we are taking this low pass filter as an ideal filter, so it must be satisfied, means the frequency response of this decimation filter, that's why we are writing it Hd omega, will be 1 between mod of omega less than equal to pi by d. So the bandwidth is from minus pi by d to pi by d. Originally bandwidth of the sequence xn is, here is from minus pi to pi, and the bandwidth of this is minus pi by d to pi by d, okay. So what happened? In this frequency range, the magnitude will be totally passed by the ideal low pass filter, otherwise it is 0. So what happened? Thus the filter eliminates the spectrum of x omega in the range pi by d mod omega pi. So you can see, like your sequence, your signal is from minus pi to pi, but when you will pass it low pass filter will only take the values in minus pi by d to pi by d. So we will get only this output. Okay. So you can say this low pass filter removes between the spectrum between minus pi to minus pi by d and pi by d to pi. So you can say your mod of omega between pi by d to pi means this interval, and mod according to mod this is minus pi to minus pi by d. Okay. So this does the filter eliminates the spectrum in this range. Of course, the implication is that only the frequency components of xn in the range mod omega less than pi by d are of interest in further processing of the signal. So why we have did this? Because when we will do the downsampling, then what happened? Our spectrum will be stretched. So if pi by d will be there, so when we will do the downsampling, it will again comes from minus pi to pi. If we will not do this, then the spectrum will be pi d to minus pi d to pi d. That is not possible actually, and due to that, what happened? There will be aliasing effect. Okay. So that's why we have taken a low pass filter which is lying in the range minus pi by d to pi by d. Okay. So from this block diagram we can see like Vn is the how we will get this Vn? Vn is the output of a low pass filter. So low pass filtering operation is basically nothing but the convolution operation. So we are convolving this sequence xn with the impulse response of this filter which is hn. So you can say Vn is nothing but xn hn convolution xn. So that's why we can write it like this: Vn equals to k equals to 0 to infinity hk into x of n minus k, which is then downsampled by factor d to produce ym. So ym will be equal to v of nd, v of md. So now we will put n equals to md in this equation. So we will get hk, and in place of x we will write md minus k, again summation k equals to 0 to infinity. Now although the filtering operation on xn is linear and the time invariant, so if we will talk about this operation from here to here when we are moving, then this operation is basically linear time invariant operation because we are using an LTI filter. Okay. But this process when we comes from Vn to Yn, this process is basically, you can say this process is basically time varying operation. Okay. So here time invariant operation is there and here time varying operation is there. So overall it will become time variant operation. Okay. So although the filtering operation on xn is linear and time invariant, the downsampling operation is combination with the filtering result in a time variant system. Means because operation is here is time invariant and here it is time varying. So overall when we will combine this, the operation will be time variant. Consequently, the overall linear operation, linear filtering followed by downsampling on xn is not time invariant, means it is time variant. Okay. Now we will see the frequency domain characteristics of the output sequence ym. So the frequency domain characteristics of the output sequence ym can be obtained by relating the spectrum of ym to the spectrum of input sequence xn. Okay. So this we have to do. First we will define a sequence, let us say v cap n as v cap n equals to vn, where n is lying between 0 plus minus d plus minus 2d, or we can take only those values which we are getting after the decimation. Okay. So v cap n is nothing but vn, where vn is an, you can say, infinite duration sequence, but here we are taking or we are interested only those values of vn wherein values are as per the value of d. Okay. So this vn is only applicable when small n will be equal to 0 plus minus d plus minus 2d. Like if we are taking d equals to 2, so we are taking the value of n from 0 plus minus 2 plus minus 4 like this. Okay. So clearly v cap n can be viewed as a sequence obtained by multiplying vn with a periodic train of impulses pn. Okay. So how we can obtain it? If we will multiply vn with a periodic train of impulses pn with period d. Okay. So vn, you can say v cap n, how you will obtain v cap n? That will be equal to vn into pn, where pn is a periodic train of impulses, and where impulses are located? Impulses are located at these values of n, so that we will get only the we will get those values at the output. Okay, now this sequence Pn, how we can define this sequence Pn? This sequence Pn can be described by a Fourier series representation like Pn equals to 1 upon d summation k equals to 0 to d minus 1 e to the power j 2 pi k n by d. Okay, and v cap n equals to Vn into Pn. So if we will calculate Ym, so Ym equals to, we have already seen Ym equals to Vmd. Okay, so in place of Vmd we will write V cap Md, and V cap Md is nothing but Vmd multiplied by Pmd. Okay, because V cap n equals to Vn into Pn, in place of n equals to Md we will write, so we will get this. Now Vmd into Pmd, and the value finally we will get is Vmd. Okay. Now the jet transform of the output sequence Ym is, so the output sequence is Ym, so how we will take its jet transform? Ym into z to the power minus m, where m is lying between minus infinity to plus infinity, and the value is yz. Okay. Now Ym equals to, we have already taken Ym equals to V cap Md. Okay, so we will write V cap Md z to the power minus m, and summation m equals to minus infinity to infinity. Now this we can also write, let us suppose capital small md will be equal to m. So if md equals to m, so we will write it m, then so m will be equal to m by d. So if we want to replace it, then we have to write it z to the power minus md, if we are writing vmd equals to this. Okay. Okay, where the last step follows from the fact that V cap m equals to 0 except at multiples of d. Okay, so this is yz basically. So yz is the jet transform of the sequence ym or the output. Okay, now we will write this equation, v cap m is equal to vm into, V cap m equals to Vm into Pm, and your Pm is this expression 1 by d summation k equals to 0 to d minus 1 e to the power j 2 pi mk divided by d multiply by z to the power minus m by d. Okay, then we can solve this summation, like we can take this portion outside, 1 by d summation k equals to 0 to d minus 1, and then we will take it summation m equals to minus infinity to infinity Vm, and this is e to the power minus j 2 pi mk by d into z to the power minus m by d. So we are having terms e to the power j 2 pi mk by d into z to the power minus m by d. How we can write it? Like e to the power minus j 2 pi k by d into z to the power minus 1 by, sorry, plus 1 by d if we are taking, then we can write it like minus m. So you can see again you will get e to the power j 2 pi mkd, and if we will take minus here, so this will become plus, sorry, this is plus if we are taking, so this will become minus. Okay, so we can write it like this, Vm this into minus m. Okay, so now here we can see that Vm into z to the power minus m, Vm, if it is Vm into z to the power minus m, then we can write it like Vz. But in place of z, what is there? E to the power minus j 2 pi k by d z to the power 1 by d. So we can write it like V of, in place of z, we can write this whole thing, e to the power minus j 2 pi k by d into z to the power 1 by d. Okay. Now we can see V of z, let's say this is z. So Vz, if we want to see this Vz, what is the value of Vz? From here we can see that Vn is xn convolution hn. Now if we will take the z transform on both sides, so you know linear convolution of two sequences is nothing but multiplication of their z transform values. Okay, so you can say if you want to write it like Vz, you can write as xz into hz. Here is the convolution, but here is the multiplication sign. Okay, so accordingly Vz equals to xz into hz. So that we have written over a Vz equals to hdz into xz. Now we want to obtain the spectrum. So you know What is the spectrum? If you are having the Z transform value, means you are having the value of Hz, and we want to calculate the spectrum, then we will put Z equals to e to the power j omega. Okay, why we will put Z equals to e to the power j omega? Because Z transform evaluated over a unit circle is nothing but the discrete time Fourier transform. Means discrete time Fourier transform is nothing but the Z transform evaluated over unit circle. So because the value of Z is equal to r e to the power j omega, and r value will become 1. So this is Z equals to e to the power j omega. So if we will write Z equals to e to the power j omega, then we will get the spectrum. Okay. So you can see here, so by evaluating yz in the unit circle, we obtain the spectrum of the output signal ym. So we will simply write Z equals to e to the power j omega in this, and we will get the spectrum. Now we will see about the rate. So since this is the rate of ym is fy equals to 1 upon ty, the frequency variable we denote as wy is in radians and is relative to the sampling frequency fy. So our sampling frequency is fy, in radians we can write it like wy, and both are related by the expression wy equals to 2 pi f upon fy. 1 upon fy is ty, so you can write it like this. Now you know, in the process of decimation, sampling rate is reduced by a factor of d. So let us suppose the output signal sampling rate is fy. So how we will write it? Fx will be divided by d. Okay, so these are related by this, since the sampling rates are related by the expression. Now if we want to calculate wx, small wx, this will become 2 pi f by fx. Okay, this you can write as 2 pi f by 2 pi f times tx. Now we will take the ratio of wy by wx. So you can write it like 2 pi f by fy into fx by 2 pi f. So 2 pi f cancel. So this will become fx upon fy. Since we know fy equals to fx by d, so wy upon wx will be equal to, according to, if you will see, fx will be fy times d. So this is nothing but d, or wy equals to d times wx. Okay, so don't confuse. Actually sampling rate, we are talking about the decimation, so we are interested in this factor. Okay, and here we are representing it in terms of radian. Okay, but you can say wy equals to d times wx. It means the spectrum in frequency domain will be multiplied by a factor of d. Thus as expected, the frequency range 0 to pi by d mod of omega x is stretched into the corresponding frequency range 0 to pi within mod of omega y, means the value of mod of omega y is lying between 0 to pi by the downsampling process. So you can see, when we did the downsampling, then what happened? Our spectrum is stretched by a factor of d. So for mitigating this, we have already passed our signal through a low pass filter having value minus pi by d to pi by d. So that what happened? If we directly apply it over here, then what happened? The spectrum of the output signal will be lying between minus pi d to pi d, due to which aliasing will be there. So what we are doing? We are passing it through our low pass filter, so that we have reduced the spectrum range by minus pi by d to pi by d, so that when downsampling operation will be there, then this will again output will get in the range minus pi to pi. So this is the reverse operation that we have done already. Okay. Now we conclude that the spectrum y omega y, which is obtained by evaluating on the unit circle, can be expressed as. So what we are doing? In this expression, we are putting z equals to e to the power j omega. Okay, z equals to e to the power j omega. In this expression, what we are getting? Y omega y. Here z equals to e to the power j omega. So this is the value, but when we are writing yz, so we are not writing y e to the power j omega, we are simply writing y omega y. We can also write it, but here we will write e to the power j omega. Okay, but again the value we are writing in this form, so again we can write it like this. So ywy equals to 1 upon d summation k equals to 0 to d minus 1 hd wy minus 2 pi k by d into x wy minus 2 pi k by d. How we are getting this? We are simply writing z equals to e to the power j omega in it. Okay, and then we will solve it. Now with the properly designed filter HD omega is our decimating filter. or the anti-aliasing filter, the aliasing is eliminated, and consequently if we are properly designed, we are doing this, we are properly designing it, so then these factors will be eliminated. Okay, so we are having wy by d into x wy by d, or you can also write it, this value will become 1, this we are getting this. Okay, so we can see the spectra using this. So this is the input signal spectra, we can say it is band limited between minus pi to pi. Okay, then we are taking a low pass filter or anti-aliasing filter or decimating filter lying between minus pi by 2 to pi by d. The magnitude is this is ideal filter. Okay, so when we are passing this sequence, when we are passing this signal with this filter, what happened, we are getting this output vwx. So mod of vwx will be this multiplied by this. Okay, so we can see this is lying between minus pi by d to pi by d due to this filter. Okay, and then we will do the downsampling. When we will do the downsampling, then this spectrum is stretched by a factor of d. So this will become again minus pi to pi. So this is the output that we are getting. Okay. So, so from figure 5 we can find that the spectrum, figure 5 is this. We can find that the spectrum obtained after downsampling overlap if the original signal spectrum is not band limited to omega equals to pi by d. This overlapping of spectra is called aliasing. Therefore, aliasing due to downsampling a signal by a factor d is absent if and only if the signal xn is band limited to plus minus pi by d. So this we have already done using this decimation filter. Okay. If the signal xn is not band limited to plus minus pi, then a low pass filter with a cutoff frequency pi by d is used prior to downsampling. Okay. So this low pass filter which is connected before the downsampler to prevent the effect of aliasing by band limiting the input signal is called the anti-aliasing filter. Okay, so this you can see here, this is the original signal spectrum. Okay, and this is the process of, if we will not do the we will not pass this sequence or signal xn through a low pass filter, then this type of spectrum aliasing will be there. Okay, so for reducing this spectrum aliasing, what we will do, we will basically band limit it to the pi by d by using a low pass filter. Okay, so this is the input sequence spectrum and this is the aliased output spectrum if we are not doing the, we are not passing our signal first of all through a low pass filter of bandwidth pi by d to minus pi by d to pi by d. Okay, so here comes to the lecture, here comes to the end of this particular lecture. Okay, I hope that you will understand the concept of decimation. Okay, thank you.